Hey there, chemistry. We are going to talk through the history of the model of the atom from way the heck back in about 400 BC until about 1913. So are you ready for this? We're going to go through about 2,300 years of history so that we can talk about the current model of the atom and how it affects chemical bonding. So here we go. We're going to start back in a debate between Aristotle and a guy named Democritus. You can see him at the bottom there. He's a looker, isn't he? He looks so happy. So Aristotle proposed this theory of the four elements, earth, water, air, and fire, and he proposed that everything was made out of these four elements. Democritus actually had an opposing theory, and he proposed that everything in the world was made out of tiny, indivisible, spherical particles, and he called those atomos. Now, Aristotle's theory took off and was held to be truth for about the next 1,500 to 2,000 years. So a really long time, way longer than our current model of the atom has been along. And the reason was Aristotle had explaining power. Democritus did not. Neither one of them had evidence that they were basing their conclusions off of, but Aristotle said things like, well, birds are made of more air so they can fly, and fish are made of more water so they can breathe underwater, and paper is made of more fire because it can burn. So his explanations had explaining power, and they were accepted and they were held to be true for a really long time. So long, in fact, that it was held to be truth and the usefulest model, if that's a word, the most useful model until a guy named John Dalton came along. So this is John Dalton. He was an English school teacher, and he did experiments with chemical reactions. And basically what he did was he would weigh them very, very carefully before the reaction occurred and after. All he did was weigh stuff. He just did it extremely well, and he would draw conclusions off of his data, off of the weights that he gathered. And he came up with some really big theories. He came up with, he basically supported Democritus's theory of the atom, and he came up with about 5 postulates of what an atom was, that all matter is made up of atoms, that they're tiny, he called them invisible, was one of his postulates, that they are indivisible was another postulate of his, and that everything is made up of them. And he also came up with a couple laws, the law of definite proportions and the law of multiple proportions. So the law of definite proportions that he kind of discovered and supported with evidence was basically that all of these elements combine in the same ratio. They always combine in ratios, and his ratios were based off of masses because he weighed stuff, right? So he would say, okay, when hydrogen and oxygen combine to form something new, they're always going to combine in definite proportions of 16 grams of oxygen to 2 grams of hydrogen. So this was his definite proportion, and it was based off of mass. Another law that he came up with was the law of multiple proportions. And the law of multiple proportions basically says when atoms combine, they can combine in multiple ways, but they always follow these set ratios. So it's 14 grams of nitrogen to 16 grams of oxygen, or you can double that and you can go 28 grams of nitrogen to 16 grams of oxygen. Or you can double it the other way and go 14 grams of nitrogen to 32 grams of oxygen. So basically what he was uncovering and what he was supporting was chemical reactions always happen with one atom or 2 atoms, but never half an atom. And this is why he said that atoms were indivisible, because you couldn't combine half an atom. If a nitrogen atom weighed 14, you could have 14 or 28 or any multiple of that, but you could never have half of that or a quarter of that or any other proportion other than 1. They always combined in their base units of 1, and these base units turned out to be their atomic masses: 14 grams for nitrogen, 16 grams for oxygen, 1 gram for hydrogen. So Dalton came up with this groundbreaking theory that atoms existed. He was right on some of his postulates. He was a little bit off on some of his other postulates, but pretty impressive to see what he did with just a scale, right? And so the scientific community started to switch over to this idea that atoms existed and they could combine and they could form new things, but the atoms were always present. And they started to move forward with this idea. Now, the next breakthrough for the model of the atom was J.J. Thomson and his cathode ray experiment. So a cathode ray looks like this little tube. It's an evacuated glass tube, and basically it has a couple charged areas, and they can shoot electrons through it. So notice that electrons start on this end and basically travel through the cathode ray tube. You have a negative cathode over on this side. And then notice that you have a negative charge here and a positive charge here. So what they noticed as they pushed these electrons through the cathode ray tube was that no matter what gas they put in this tube, they could always deflect the little particles that were going through the tube. They could deflect them with this positive and negative charged plates. And these little particles that were coming off of every single gas that they tried were always attracted to the positive side, and they would kind of bend down and strike the tube in a different area. They were repelled from the negative side. They would bend down and strike the tube in a different area. So what J.J. Thomson came to the conclusion of was that the atoms, in fact, are divisible, that there must be little particles inside of these atoms because we can pull off the negative ones, and no matter what gas we try, this is always true. So all atoms must have these negative particles inside of them. And if they have negative particles inside of them and they are themselves neutral, then they also must have positive charges inside of them. So J.J. Thomson proposed a slightly different variation of Dalton's atomic model, and he called it the plum pudding model. And that is because basically, he had all these little particles that he had evidence for, and they were all just kind of mixed up into the atom. So we called it the plum pudding model. It's a model of the atomic, of the atom. It's an atomic model that has little particles inside of them. So we have Dalton, who proposed the idea of atoms. We have J.J. Thomson, who proposed the idea of subatomic particles inside the atoms. And then our next one was a guy, was done by this lab who was headed by this guy named Rutherford. And what he did, in his lab did, was called the gold foil experiment. So this is the gold foil experiment. And basically what they had this alpha particle source. Now an alpha particle is a very highly charged positive particle that is also fairly heavy. So basically, an alpha particle is a helium nucleus. The helium nucleus is going to have 2 protons and 2 neutrons in it. So it's going to have a mass of 4, and it's going to have a charge of a 2+. So it's pretty charged and it's pretty massful. And they are going to shoot this alpha particle through a very thin section of gold foil. And what they expected to see was up here in the pink. So if you're shooting these highly charged, very heavy particles through this mass of teeny particles with hardly any mass at all and not as much charge, what they expected to see was all of them would just blow through. And what happened was most of them just blew right through. Most of them did actually hit on this side where they expected to find all of them, but a few of them actually got deflected by the gold foil, and some of them actually bounced back. And how Rutherford described it was, it was like shooting a cannon at tissue paper and having the cannon bounce back. You should never have a situation where a cannon cannot blow through tissue paper unless your understanding of tissue paper is off. And they had to think about this experiment. I'm sure they redid it a million times because they figured that it was their error. And they always got the same results. And so eventually, after about a year of kind of pondering this and talking about this, what they concluded was there must be something in that gold foil that is bigger than a helium atom. So it weighs more than 4. And more highly charged than a helium atom. And so what they proposed was that all of the positive charge in the atom was actually centralized in the middle of the atom, and they called it a nucleus. And then the electrons were still out here making up the rest of the size of this atom. And that would be enough to explain why most of them did blow through. Most of the alpha particles did hit these electrons and just blew right through them, but some of them actually hit the nucleus, and the nucleus was full of mass and charge enough so that it could bounce the helium atom nucleus, the alpha particle, backwards. And so Rutherford proposed the nuclear model of the atom, and the nuclear model of the atom was accepted and moved forward until about 1913, when Niels Bohr came on the stage, and Niels Bohr started looking at the structure of the electrons around the atom. And Niels Bohr was actually a physicist. And so here's where chemistry and physics start to collide. Niels Bohr studied light, actually. And what he noticed was when charged, when electricity was run through atoms, certain gases, the gases always gave off the same light. Now, this was not a discovery by Niels Bohr. Niels Bohr just took this phenomenon and thought about it and studied it and worked with it, and he applied math to it. So when electricity is run through hydrogen gas actually gives off light. And in fact, most atoms do this. Most atoms, when you run electricity through a tube of this gaseous atom or element, the element will actually give off light. And you can see the light that hydrogen gives off. Now, the interesting thing is that hydrogen is what Bohr was focused on. And hydrogen always gives off this light no matter what its source is. You could collect hydrogen by splitting water and it gave off the same light. You could collect hydrogen from the atmosphere and it gave off this light. You could collect hydrogen from a reaction with hydrochloric acid and it gave off the same light. The element of hydrogen always gave off this light. It was so consistent and so patterned. Niels Bohr started studying it and trying to describe the pattern, describe the light that was given off by hydrogen using equations, using math. And what he built was based off of wavelengths. So follow me here. We all know that a specific light, like this light that's around 650 nanometers, has a specific wavelength. Okay, so this one has a very specific wavelength. It's somewhere around 650 nanometers. Well, if it has a specific wavelength and it has a specific speed, it also has a specific frequency. And we just looked at this equation. We know that speed and wavelength and frequency are all related, and we can calculate between them. Okay. What we haven't talked about is that frequency is also related to energy. Energy equals H times nu. So this H is just a constant It's called Planck's constant. It's, in case you want to know the number, 6.624 times 10 to the negative 34th joule seconds. Okay, so what is a constant in an equation? A constant is just a number that's in an equation that makes the equation work. And so he noticed that he didn't notice, but scientists at that time noticed that there's a relationship between energy and frequency, and that relationship was always in the same proportion. And so if they took that proportion and entered it into the equation, you could actually come up with an equation where if you know the frequency, you can calculate the energy. And if you know the energy, you can calculate the frequency. So now we have a way to calculate between wavelength, speed, frequency, and energy. And so what Niels Bohr proposed was that energy corresponded to the energy an electron would need to absorb in order to move to another energy level. So he thought electrons are not just scattered willy-nilly around an atom. Electrons are actually at very specific distances to the nucleus. So this little black dot is the nucleus, and this is an electron. The little green dot is an electron in the second energy level. Okay, and if the electron wanted to move from the first level to the second energy level, it would have to absorb this amount of energy in order to move that level. And if it wanted, so this would be times energy. If it wanted to move to the second energy level, it would have to absorb 2 times that amount of energy. And so what Niels Bohr proposed was that this energy could correspond to a very specific distance between the nucleus and the electron. And that distance was where the electron had to circle the nucleus. And what he called this very specific distance where the electron was required to circle the nucleus, he called them orbits. And the electrons could absorb energy and move farther and farther away within the multiples of the energy. It could absorb 1 quantity of the energy, or it could absorb 2 quantities of the energy, but it couldn't absorb a half a quantity of the energy. So there were these required distances that the electrons moved. And Einstein actually took this idea and ran with it. And he said he called this specific quantity of energy, he called them packets of energy or quantums of energy. It was a very specific quantity of energy that the electron could absorb and move a specific distance away. And he called those packets of energy, he called them quantums of energy. If those packets of energy are light energy, we call those photons. And so Niels Bohr, in this way, gave structure to the electrons around the nuclear atom. Now, Niels Bohr wasn't completely right, and we'll talk about what specifically changed between Niels Bohr's atom of the model and our current atom of the model called the quantum mechanical model. But before we do that, we're going to look into this model, this Bohr's model of the atom, of the hydrogen atom, because this model actually is really useful to us as chemists. It can help us understand where the electrons are. It can help us understand why the electrons move and what happens when they move. It can help us understand bonding between the atoms in the formation of compounds. So we're going to look at Bohr's model and kind of pull it apart a little bit here in the next couple days so that we can understand the behavior of the electrons and the movement of the electrons in order to go into bonding. So let me know what questions you have. Welcome to abstract chemistry, and I will see you in class.